Welcome everybody. I talk a little bit about benchmarking and capturing memory metrics. Oh, it was wrong. I'm Jens. I'm actually doing e-business, e-commerce applications in Java since 1999. And sometimes I like to dig a little bit deeper into things and like to solve things at the right place. And I'm also a performance fanatic, and that's brings me to the topic of caching. And I write a caching library which is called Cache2K. And so this is like my major topic of interest. And because of that, I do a lot of benchmarking. So that's the outline of the talk, a little bit of motivation, and how can we gather different memory metrics from the JVM, and or how can we not gather it while running a JMH benchmark. And then I present some results, and then there is some happiness and maybe confusion. Okay. If there is any confusion or some question, rise up, please, straight away. So, why I'm doing this? There are a lot of libraries with caching out there, and everybody says like, we are high performance. I'm German, I'm always a little bit more accurate and a little bit more detailed about things. So before I say I am high performance, I better check that. I use JMH for benchmarking for a couple of reasons. I'm not going into detail about this. This is actually a whole other topic. When you do JMH benchmarking, throughput benchmarking, the primary result, the primary metric you get is operations per second. And this is quite nice. And there are JMH profilers that lets you collect a lot of other metrics. But actually there is nothing that lets you collect the memory usage right now. But when I do benchmarks about a caching library, then how much memory is used is actually quite essential, because caching library is actually a thing to tune the time and space trade-off. So with caching, you can always trade in memory for faster speed. So, what are the different opportunities to get memory information? One thing that people are doing is object graph traversing. There is some libraries from EHCache and something that is called Java Agent for memory measurements. So what is happening is that you give those libraries a root object, and then they traverse like a scan, a depth scan into the object hierarchy via the references, and then there is some magic, sometimes with some misc unsafe happening to get the size of an object, and then this is summed up, and then you have a result. This is quite nice because you can just like fill your data structures and then ask the library, okay, how much memory this is going to cost me. So you can integrate it in continuous integration and get some results out of it. But it also only covers like a partial set of the memory. And the other problem is like, how much is actually traversed? Do I want, like, how do I keep the thing from traversing the whole heap? And of course, it's the heap only, and it's only like a static result, and not does not cover what's happening when the program is actually running. The other thing what you can do is a heap dump or a heap histogram via JMap, for example, and count all the objects and get a metric how much data they about the memory size. And yeah, it's actually same as before, but it's a bit costly, especially the heap dump, and again only a static result. So what's happening when I run a Java program? So this is the output of Visual VM. When you click Monitor and Heap, then you see the space allocated by the objects in blue. That's the heap that moves up and down each time the garbage collector does its work. And the orange thing is the total memory that is occupied. So how does this relate to my JMH benchmark? JMH is spinning up a JVM, running its benchmarks in there, and then there are iterations, and you can specify how much iterations you want to do for warming up your workload, and you can specify how much iterations you want to do for actually measurement. In this case, I do 2 iterations for warming up and 3 iterations for the measurement. So when I want to know how much heap I use, I can take a look, and then I get like interesting values. It could be like down here or up there. So no idea. Yeah. So one idea you might have is, let's force garbage collection after each iteration. So I filled the data structures, did some warm up, and then let's force the garbage collector, and then take a look what's left on the heap. Then we have a consistent metric about the heap space. But when you compare the 2 runs of the benchmarks, one with no forced garbage collection and one with the forced garbage collection, you see that it's actually quite different in the shape. So you're actually interfering a lot with what the garbage collector is doing and how would the JVM react naturally if you just let it do its things. So yeah, one short thing. Who is actually working with JMH? Okay, yeah, a couple of guys. Okay, that's great. So is there any remark to this picture here from people knowing running JMH? Is there anything interesting? So the thing is, so these 3 iterations are my measurement iterations, and we see that actually the garbage collector here is still expanding. So with iteration 1, 2, 3, we are actually not running at a steady pace. The garbage collector is not, is not yet at a stable memory size. So what might happen is that our results in the different iterations are quite different between the iterations because the garbage collector is still expanding. The other interesting thing is that we have about 2 garbage collections happening within the iterations, and this might be a problem as well, because maybe there are 2 happening, there are 3 happening, maybe just 1. So it's interfering with our throughput measurement result a lot. So as a general thing, I would say like there are two kinds of micro benchmarks here. There are like the real micro benchmarks, the micro benchmarks, where a garbage collection cycle might happen occasionally, but in this case, you probably want to get the garbage collector out of the equation of your measurement. You can do this by forcing a garbage collection before your iteration, or maybe even use the Fore GC that is new now. And yeah. However, when you have like a not so micro benchmark, then and the garbage collection cycle is happening a lot during your iterations, then yeah, actually you want it to happen like a lot, that it's not interfering too much with your measurement results. And you better know what your garbage collector is doing, or the other way around, by monitoring what the garbage collector is doing and how much memory your JVM is using. You get to know what your garbage collector is doing a lot more. So if you cannot avoid the garbage collection, you actually want to make it go steady during the iteration. So yeah, so what kind of metrics I can extract here? So what I did implement is use the things that the operating system is giving us via proc self status. There are two things of interest here. This is the residence set size, and there is also called the high watermark, which is actually the highest level of the residence set size a process had in its run. So these are two nice metrics. You can use garbage collector notifications. You actually get a notification from the garbage collector each garbage collection cycle, and you get some information about the used memory before the garbage collection and after the garbage collection. And I take the maximum of that and add it to the JMH results. Yeah. And a good also feature is the allocation rate, which you should keep look at. So this is actually the rate, how many objects are allocated. You get this. This is actually built in JMH with the garbage collector profiler. And then finally, I decided, like, when we are finished with our iterations, then it's safe to do a forced garbage collection and use JMap to get a heap histogram, and also use the management extension to get the value of the used heap. So here's the example of the running scheme I use for the upcoming examples, results. So JMH has a control process, and from that control process, it forks the measurement JVMs, and you can say how many forks JMH should do. And so in each measurement JVM, there's a warm-up iteration. There are warm-up iterations and measurement iterations, and those fork JVMs run one after the other. So actually I have altogether 9 measurement iterations here. And so from the primary metric, I get 9 results after each iteration. For the memory metrics I gather with the forced garbage collection, I only get free, because this runs at the end of the fork. So here are some results, but first I need to explain the benchmark that I'm doing. I walk you through. So first, here there is, for each thread, I use a fast Zipfian sequence generator. This is actually a skewed random pattern that yields about 90% hit rate in the cache with this configuration. It's, yeah. Oh, I see, here's a mistake. I actually do it with 1 million entries. And here's the benchmarked operation. It's actually a cache get. And whenever the entry is not in the cache, loading function is called. And this loading function is actually using a JMH feature called black hole consume CPU. So there's a heavy penalty when you have a cache miss. So this means there's a lot of things happening on a single operation, the cache get, and there's some cache eviction, data structures, and garbage produced, and also some auto-boxing. That's the benchmark setup, the environment. It's a machine with 4 physical cores. I limit the core usage. I'm not using hyper-threading via CPU hot plugging. The benchmarks runs with 4 threads. I tested with the Oracle JDK 11 with Parallel GC and G1. And for reference, there are the versions of the libraries. These are the JMH parameters. I already talked about it. Free measurement iterations, 3 forks. Gives 3 measurements, 9 measurements, iterations altogether, and 60 seconds iteration time. The graphs show the confidence interval in the error bars, and JMH uses a 99.9% confidence level, which is pretty tough. So these are the performance results. Like the cache-to-K cache implementation comes with 7 million operations per second. But this is actually not what I want to talk about. Let's look at the memory usage for the parallel garbage collector. And here is the heap usage, the different metrics. The first one is via JMap and histogram. The second one is after I run the garbage collector. And yes, and the third one also, and the second one is the used heap, and the third one is the total used memory. So not only the heap, but also the non-heap memory. And here's something astonishing, that the histogram actually reports more used memory than the management extension beans. We also see that the error bars here are, like, there's a lot of variance in the results here. Let's look at the resident set size. So what's the operating system giving us? And from the very right, this one is the high watermark metric, so the highest resident set size. Then this is the resident set size at the end after the garbage collection. And this is the highest amount of committed memory the garbage collector reported after the garbage collector run. And this is the total committed memory that the JVM is reporting. We see sometimes there is a lot of variance, and But actually, those values are quite close together. Also, when I go back here, we see like those values are also quite close actually together. So when we are not like debugging the garbage collector, we are fine just looking at one of these values. Oh, so let's take a look at the G1 garbage collector. Here, the result of the histogram is more consistent with the thing that the VM is reporting via the management extensions. It's pretty much on the same level. And what is interesting is now that the memory, the actual used memory by the operating system is differing a lot between the caching implementations and also between what the operating system is reporting as the high watermark level and the resident set size at the end of the run after the forced garbage collection. So here we get a lot of different results. The reason why we get a lower resident set size is that G1 is giving back aggressively memory to the operating system. So the high watermark is different. And the other thing is why now there are a lot of different results for G1 is that actually we are doing here a throughput benchmark, and G1 is actually not intended for highest throughput but for low pause. And this is, we see here actually the toll we're going to pay for that. And because what is happening is that the allocation rate between the implementations is quite different. And the higher the allocation rate here, there's a correlation to the used memory. So, and this is the allocation rate per second. Oh, this is wrong here. So this is the allocation rate per second, and this is the allocation rate normed by the operation in bytes per operation. So let's wrap it up. When garbage collection is happening, it's good to keep an eye of your memory usage. There are various metrics you could record that have varying degree of accuracy and meaning. And when the garbage collection is happening and you're not having like a real micro benchmark maybe, then you need to run your benchmarks longer, and the more heap you have, the longer you need to run your benchmark iterations for the garbage, to give the garbage collector time to swing in. You can actually use JMH also to construct benchmarks to evaluate your memory usage. Be aware of the different garbage collector implementations and their behaviors, or explore the different garbage collector behaviors. And the plan and idea is to see and include those metrics in the JMH code base. The code that I did is available on GitHub at the Cache2K benchmark project. Those are the two classes. And yeah, if you like to have a fast cache, then look at Cache2K. And yeah, thanks a lot. Enjoy life. Any questions? Yes?
Do you have any integration into CI to observe memory consumption?
Can you repeat the question, please?
Yeah. You mean, is there an integration into continuous integration, or? I'm actually doing it, but not in CI, because it's a little bit tricky. You need to have the hardware exclusively if you want to have accurate results. And even I don't trust like a Jenkins process or anything running on the machine or doing like network traffic and things like that. So it's a little bit tricky to do it right, but it's a good idea to do it, of course.